All right, here we got the notes for section 4.7, deals with the inverse trigonometric functions. So the inverse trig functions take a value and return the angle that generated that value. So we'll start with the inverse sine function. So there's some unique angle y in the interval negative pi over 2 to positive pi over 2, which means, what the interval means is that your inverse sine function has to come from either quadrants 1 or quadrant 4, because this is negative pi over 2. This is positive pi over 2. So or degrees negative 90 and positive 90. So we're only allowed to look in these two quadrants if we're using the inverse sine. So it says the domain is negative 1 to 1, because those are the values that sine stays in between. And the range is negative pi over 2 to positive pi over 2, because we're not allowed into quadrants 2 or 3. So the easiest way to do this is honestly to look at the unit circle and look up the values. So remember, sine is the y value on the unit circle, so the inverse sine of 1/2 is where in quadrant 1 or 4 does the y value have 1/2, and that's at 30 degrees or pi over 6 radian. Negative 3 pi over 2, the next one, is going to be down here. That's actually, now you have to be careful because you're counting negative angles. So if you're doing inverse sine and you don't have to worry about thinking about the negatives, ignore this negative sign for now and find the inverse sine of 3 pi over 2, which is up here at pi over 3. But since it's negative, it's going to be negative pi over 3. So they have to rotate down instead of up. This inverse sine of pi over 2, this is no solution because pi over 2 is more than 1, so I can't take the inverse sine of it. There is no angle that has an inverse sine of 1.57. The inverse sine of the sine of pi over 9, well, pi over 9 lies in quadrant 1, so it actually is just pi over 9 times, because these are inverse functions, they end to each other. Now, that's true if the angle's in quadrant 1 or 4, but if it's in quadrant 2 or 3, you have to be careful. So the inverse sine of the sine of pi over 6, well, sorry, the sine of 5 pi over 6 is actually 1/2, which means that this is actually the same problem as our very first example. This is pi over 6. So for an angle's in quadrants 2 and 3, the inverse sine function reflects it and puts it back in quadrant 1 if it was in 2, or 4 if it was in 3. So down here, calculate in radian mode to evaluate these. So let's make sure my calculator is in radian mode. Yep, okay. So let's see here. Inverse sine, inverse cosine, inverse tangent can all be found. They're the shifted versions. So there's inverse sine, and then I just type in negative 0.81. So I'm in radian, so this is negative 0.9, we'll say 44 radian. So down here, let's try this one. So the inverse sine of the sine of 3.49 pi is negative 1, there we go. So negative 1.539. That's my answer. No degree symbol because these aren't degrees, they're radian. Okay, so we've got the inverse cosine, inverse tangent functions. So cosine, if you're looking for cosine, cosine comes between 0 and pi, and tangent, so in quadrant 1 or 2. Tangent is the same as the sine, it's from 1 or 4, but down here we're using negative angles instead. We don't use, because otherwise they can't. The reason this has to be negative pi over 2 and not 3 pi over 2 is that the way numbers work, you can't stay between 3 pi over 2 and pi over 2. That doesn't make sense. 3 pi over 2 is more than pi over 2, so it would actually be reflecting, you'd be doing these two quadrants. So that's why you have to make this a negative value. All right, so for cosine, cosine is the x values. So in this case, the inverse cosine of negative root 2 over 2, I'm looking for it in quadrant 1 or 2, whereas the x value, and that's actually at 3 pi over 4. The inverse tangent of root 3, that's in this quadrant. It is actually the 60 degrees, which is pi over 3. Note that if I put this in my calculator, the inverse tangent of the square root of 3, I get that. If I do, oops, well, now I'm going to be in trouble. So the inverse tangent of the square root of 3, and So that's the decimal, pi divided by 3. So same value, but notice it says exact value, so you cannot use the calculator number. All right, so the inverse cosine of the cosine of negative at 1.1, so that would be in quadrant 2, which I'm allowed to do, so this is just negative 1.1. Describe the end behavior of the function, the inverse tangent of x. So if you look at the graph, because end behavior is easiest to see if you look at the graph. Oh, don't need these guys. So let's see here. Inverse tangent of just x. Oop. View window. Reset this. Actually, we'll go to the trig mode. So it looks like this. So it's going out towards, what is this? We'll trace it. So it's going out here. So it actually will not level off. It keeps growing forever. But let's see if there actually is a value that works. Oh, so it's pi over 2. That's what I thought. Oh, so I'm looking at the y value. Sorry, I was looking at the x values. So this stays. So if I go to, oops, off the screen. If I go to positive infinity, this becomes positive pi over 2. If I go to negative infinity, this becomes negative pi over 2, which makes sense because those are the boundaries on the tangent function. So if you compose a trig function with its inverse, they tend to cancel out. So these are always true, the sine of the inverse, the cosine of the inverse, the tangent of the inverse. However, the reverses are not always true, as long as you stay within the original ones that are valid. So like if x is in quadrant 1 or 4, then this also works, but you have to be careful. You can't just assume that they automatically cancel each other out, which we saw in one of the previous examples where it flipped the angle across. Okay. So, example 5, compose each of the 6 basic trig functions with the inverse sine of x and reduce the composite function to an algebraic expression involving no trig functions. So, what we're doing here is we're going to have to build a triangle in order to do this. So the inverse sine of x, so here's x, here's 1, because its sine is opposite over hypotenuse. Which means I can find this side using Pythagoras. So a squared minus b squared, take the square root. So that's 1 minus x squared. My angle's down here, theta. So compose the right function with the inverse sine. So let's see here. So we've got the sine of the inverse sine of x. Well, that's just x. So the cosine of the inverse sine of x is, so here's my triangle, oops, adjacent over hypotenuse. This is square root of 1 minus x squared. Tangent of the inverse sine of x is opposite over adjacent, so x over root 1 minus x squared. And then to get the other ones, so let's see here, this would be cosecant of the inverse sine of x. Well, this can be the reciprocal, so it's 1 over x. The secant of the inverse sine of x is the reciprocal, 1 over root 1 minus x squared. And the cotangent of the inverse sine of x is equal to the reciprocal of this guy, so square root of 1 minus x squared over x. Now notice once we built the triangle, this part here doesn't really matter because it's going to return an angle. So I'm using the inverse sine to build the triangle, opposite adjacent. So please remember this essentially is true. So the inverse sine of x is equal to theta, which means sine of theta is x, which is how I got my x over 1. So this essentially becomes the sine of theta, x over 1. The cosine of theta, adjacent over hypotenuse. The tangent of theta, because that's what inverse sine of x is. It's the angle. All right, last one here. The bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. As you move away from the wall, the angle formed by the screen in your eye changes. Is there a distance from the wall at which the angle is the greatest? What is that distance? So essentially what's happening is you're looking up. So bottom of a 20-foot replay screen is 45 feet above the ground. And you want to know what this distance is in order to make theta as large as possible. So, stretch my arm here. So let's see here. So the angle that I'm looking for, so I have to treat this as two separate triangles actually. So I have this big angle here, we'll call that theta 1, that theta 2. So the angle I'm looking for is theta 1 minus theta 2, the difference between the big and the small. Now, because it's a triangle, I can actually, we'll call this actually x just to be consistent. Theta 1 is the inverse tangent of 65 over x, because it's this whole side divided by that unknown. Theta 2 is the inverse tangent of 45 over x, because it's just this vertical piece. Theta 2 only runs from here to here, so that's opposite and adjacent is my unknown. So this is the angle I'm looking for. Now this is algebraically kind of tricky, but I can actually draw the graph and use that to find the answer. So the inverse tangent of 65 over x minus the inverse tangent of 45 over x. Whoops, not 45x, 45 over x. If I draw this, excuse me, zoom, let's try auto and see if we get anything better. Not quite. We'll zoom out. You're looking for a peak. If you notice the graph, looks like we can see it flattening out. Let's keep going out. Oh, there, now you can see the peak right there. So on my calculator, I can hit gsolve max, and I'll find that value for me. So the x value is 54.1 feet. And the angle is 0.18 radian. So the widest the screen will appear to my eyes is 0.2 radian, and it occurs 54 feet-ish away from the screen. So there you go. That's the end of the section.